Hello students. In the last class, we had briefly discussed about the term molecularity for the elementary reaction as well as in the case of complex reaction. So molecularity is generally defined as the number of reacting molecules which are taking part in an elementary reaction which must collide simultaneously in order to bring about a chemical change. So, in the case of elementary reaction, the molecularity is simply calculated by adding the number of molecules of the different reactants which are present in a balanced chemical equation. But in the case of complex reaction, the reactions which are taking place in more than one step or the reaction which are involving more than 3 reacting species, the term molecularity has no significance, because in the case of complex reaction, the simultaneous collision between 4 or more reacting species are not favorable, and in such case the reaction which are taking place in more than one step, each step is named as the elementary step, and with respect to each elementary step we are going to calculate the molecularity of the reaction, and each elementary step involve the simultaneous collision between 2 or 3 reacting species. So students, in the case of complex reaction, the reaction which are taking place in more than one step, the question arises here is that how can we express the rate of the reaction in the case of complex reaction? In the case of complex reaction, when we are going to express the rate of the reaction on the basis of balanced chemical equation, then this term has no significance. It means in the case of complex reaction, the rate equation is written on the basis of the experimental results. Let me explain this with the help of an example, that is the reaction of nitrogen dioxide with fluorine to give nitrogen dioxygen fluoride. Okay, on the basis of the theoretical concept or on the basis of the balanced chemical equation, how can we express the rate equation? That is, the rate is equal to rate constant concentration of NO2 raised to power 2, because here the stoichiometry is 2, and concentration of fluorine is raised to power F2. But as we already explained you that in the case of complex reaction, the reaction which are proceeding in more than 2 steps, the rate equation is only expressed on the basis of experimental results. So on the basis of experimental results, the rate equation can be written as, that is, the rate is observed that it is directly proportional to NO2 raised to power 1 and fluorine, concentration of fluorine also raised to power 1. So students, after this we come on conclusion that what is the rate law? It means the mathematical expression in which the concentration which actually influence the rate of the reaction is named as the rate law. So in the case of complex reaction, the reaction which are proceeding in more than one step, the slowest step is named as the rate determining step, is named as the rate determining step or the rate controlling step, because the reaction cannot proceed faster than the slowest step. So with the help of an example, that is the decomposition of dinitrogen pentoxide, on thermal decomposition it gives nitrogen dioxide plus oxygen, and on balancing this we get the 2 mole of dinitrogen pentoxide give 4 mole of nitrogen dioxide plus oxygen. On the experimental studies, it is found that this reaction is proceeding in 2 steps. That is the step 1. In the step 1, the 1 mole of dinitrogen pentoxide give the product, that is nitrogen dioxide plus nitrogen trioxide. Here the nitrogen trioxide is an intermediate which involved in the second step, that is the step 2, and in the second step another mole of dinitrogen pentoxide combined with nitrogen trioxide, which is the intermediate which is formed in the first step, and after the reaction it gives 3 mole of NO2 plus O2. So after experimental results, the evidences suggest that the first step is the slow step and the second step is the fast step. So as I have already tell you that the slowest step in the case of complex reaction is the rate determining step or the rate controlling step. So the rate equation for this reaction is only written on the basis of the first step, that is the slowest step, that is the rate is equal to rate constant concentration of N2O5 raised to power 1. So students, after that we come on conclusion that in the case of complex reaction, the slowest step is named as the rate determining step and the rate controlling step, and on the basis of slowest step only we can write the rate law expression. Next is order of a reaction. In the last class, we had studied about the molecularity, and the molecularity is calculated from the balanced chemical equation, whereas the order of a reaction is defined as the sum of powers of the concentration terms in the rate law expression. So what is the order? The order is an important parameter of a chemical reaction. It is always determined experimentally and cannot be written from the balanced chemical equation. To understand the concept of the order, let me take an hypothetical reaction, that is small a capital A plus small b capital B. On combination, on reaction it give the product, that is small c capital C plus small d capital D. Here the A, B are the stoichiometric coefficient of the reactant A and B respectively, and C, small c and small d are the stoichiometric coefficient of the product capital C and small c. So after the experimental studies, it is found that the rate equation for this reaction can be written as the rate equation for this reaction can be written as, that is the rate is equal to rate constant concentration of A raised to power m and the concentration of B raised to power n. So with respect to this rate equation, how can we calculate the order of the reaction? So from the definition, the order of the reaction is the sum of the powers or the sum of the exponents to which the concentration terms are raised in a rate law expression. So the first point is the order for this reaction. The order is equal to m plus n. Okay, the order for this reaction is equal to the power of A, that is m, and the power of B, that is n. So it is m plus n. The second point noted here is that this m and n has no relation with the stoichiometric coefficient of A, that is small a, and the stoichiometric coefficient of capital B, that is small b, because this m and n are calculated experimentally, whereas the stoichiometric coefficient, that is the small a and the small b, are derived from the balanced chemical equation. So the third point noted here is that the order with respect to A is m and the order with respect to B is n. So again, first point is, for any type of chemical reaction, from the given rate law expression, we can calculate the order of the reaction simply by adding the powers or exponent to which the concentration terms are raised in the rate law expression. So here the concentration terms are raised to power m and n. So simply the order of the reaction is m plus n. Second is this m and n has no relation with the stoichiometric coefficient, that is small a and small b. And the third point noted here is that the order with respect to m is a and the order with respect to b is n. After that, we come to the next point, that is, on the basis of order, the reactions are further classified into first order reaction, zero order reaction, second order reaction, third order reaction, or fractional. It means the molecularity cannot be in zero or fraction, but the order of the reaction can be in zero or in fractional form. So first, explain about the first order reaction. First is first order reaction. Okay, the reaction in which the sum of powers or the sum of the exponents which are present in the rate law expression is equal to 1. That is, the rate is equal to K, concentration of A is raised to power 1. That reaction is a first order reaction and it follow the first order kinetics. And for this we take a general example that A on reacting give the product. For this reaction we can write the rate expression, that is rate is equal to K, concentration of A is raised to power 1, and here the concentration is raised to power 1 means sum of the powers of the concentration which are present in the rate law expression is equal to 1. That reaction is named as the first order reaction. Here the order is equal to 1, and the example of the first order reactions are, the first is the decomposition of hydrogen peroxide to give H2O plus O2. Okay, on the basis of experimental studies, the rate equation for this reaction can be written as the rate is equal to K H2O2 raised to power 1. So the order for this reaction is equal to 1. The second example of this reaction, first order reaction is, that is the decomposition of dinitrogen pentaoxide to give 4 mole of nitrogen dioxide plus oxygen. Okay, on the experimental studies it is found that the rate is equal to the rate constant and concentration of N2O5 raised to power 1. So the order for this reaction is equal to 1. So these are the example of first order reaction in which the sum of powers of the concentration terms in the rate law expression is equal to 1. Second is the second order reaction. After that we come on the second order reaction. Here second order reaction, here the sum of powers of the concentration terms which are present in the rate law expression is equal to 2, and the example is, the first is, and for this the rate is equal to K, concentration of the reactant A is raised to power 2. Okay, here the concentration term is raised to power 2 or the exponent of the concentration is equal to 2. So this reaction comes under the second order reaction, and the example of this first is the formation of hydrogen iodide by the reaction of hydrogen with iodine, and on experimental studies we found that the rate of the reaction is equal to rate constant, concentration of H2 and concentration of I2. Okay students, then for this reaction the order is equal to, here 1 and 1, that is 1 plus 1 is equal to 2. It means the order for this reaction is equal to 2. Second example is nitrogen oxide when combined with ozone to give nitrogen dioxide plus oxygen. Okay, for this reaction on the experimental studies we found that the rate of the reaction is directly proportional to the concentration of nitric oxide raised to power 1 and the concentration of ozone also raised to power 1. It means that here the 1 and 1, that is the order for this reaction is equal to the concentration raised to power 1 plus 1, that is equal to 2. So these are the example of second order reaction. After that we come on the next, that is the third order reaction. And for the third order reaction the rate equation can be written as, next is third order reaction, and for this the rate equation is written as rate is equal to K, concentration of the reactant A is raised to power 3. Okay students, and the example of the third order reaction is the oxidation of nitrogen oxide to give nitrogen trioxide. Okay, this is the example of third order reaction, and the experimental study shows that the rate of the reaction is directly proportional to the concentration of NO raised to power 2 and the concentration of oxygen is raised to power 1. So for this reaction the order of the reaction is equal to 2 plus 1. 2 plus 1 is equal to 3. Okay, after that we come on the next, that is fractional order reaction. Since the order of the reaction is determined experimentally. So the order of the reaction may be in the fraction form or it may be in 0. So the example of the fractional order reaction is the carbon monoxide when combined with chlorine to give carbon oxychloride, and the experimental results show that the rate of the reaction is equal to the rate constant into the molar concentration of carbon monoxide raised to power 2 and the molar concentration of chlorine raised to power 1 by 2. And after that we calculate the order. What is the order of the reaction? The order of the reaction is sum of the powers of the concentration terms present in the rate law expression, that is 2 plus 1 by 2, that is 2 plus 1 by 2 is equal to 2.5. After that the next reaction is zero order reaction. Next is zero order reaction, and the example is the decomposition of ammonia over the metal platinum or gold to give nitrogen plus hydrogen. Okay students, another example is the decomposition of phosphine on the surface of molybdenum to give phosphorus plus hydrogen. These are the example of zero order reaction. Then how can this reaction is a zero order reaction? To explain this decomposition reaction is carried out on the surface of metal, and in this case in the case of first reaction, this reaction is catalyzed on the surface of the metal, that is platinum or gold. At very high pressure, the surface of the platinum or gold is completely covered by the ammonia molecule. So at that particular condition, when we are going to further increase in the concentration of the ammonia, or when we are going to further increase in the pressure of the ammonia, then in this reaction it does not changes the rate of the reaction. So at that particular condition, the rate of the reaction become independent on the concentration of the ammonia, and after that we observe that the rate become independent on the concentration of ammonia, that on the concentration of ammonia is raised to power 0, that is the rate is equal to K, concentration of ammonia is raised to power 0, and it follow the zero order kinetics. After that again I would like to explain this. At very high pressure, since this reaction is catalyzed on the surface of the metal, that is platinum or gold, at very high pressure, the surface of the platinum or gold is completely covered by the ammonia molecules. So at that particular condition, when we are going to further increase in the pressure of the ammonia, or when we are going to further increase in the concentration of ammonia, the rate of the reaction does not changes at that particular condition. It means at that particular condition, at very high pressure, the rate of the reaction is independent on the concentration of the ammonia. So at that particular condition, the rate become independent on the concentration of ammonia, that it follow the zero order kinetics. Similarly, in the case of phosphine also, this reaction is carried out at molybdenum, and the reactions are catalyzed at the surface of molybdenum. So at very high pressure, the molybdenum surface is completely covered by the phosphine, and when we are going to further increase in the concentration of phosphine or further increase in the pressure of phosphine, it does not change the rate of the reaction, and at that the rate of the reaction become independent on the concentration of the phosphine. So these are some of the important examples of the zero order reaction, first order reaction, second order reaction, and third order reaction. After that, here a question arises that is it possible to have a reaction of fourth order? So usually a reaction of fourth order is very rare, because the simultaneous collision between 4 or more reacting species are not favorable. So the reactions with order 4 or more is very rare, and out of these, one of the example of the fourth order reaction is the decomposition of KClO3 to give KClO4 plus O2. Okay, in this the rate is equal to K concentration of potassium chlorate raised to power 4. So usually the reaction of fourth order is very rare, because the simultaneous collision between 4 or more reacting species are not favorable. It is impossible to simultaneously collide 4 or more reacting species. However, the reaction with fourth order is very rarely seen, and out of this, one of the example of the fourth order reaction is that is the decomposition of potassium chlorate to give KClO4 plus oxygen. After that, we come on the next topic, that is how we calculate the unit of rate constant for the reaction with different order. Okay, the unit of K for reactions of different orders. Okay, the unit of rate constant for the reaction of different order. First, for zero order. How we calculate the unit of rate constant for zero order reaction? That is, the rate equation for the zero order reaction can be written as, that is, K concentration of A is raised to power 0. Okay, or we can write it as, that is, dA by dt. The differential rate equation for this can be written as dA by dt. For the general example, that is the A on reacting give the product. Okay, so any quantity raised to power 0 is equal to 1. So the rate is equal to K. It means the rate constant has the unit of rate of the reaction, which is mole per liter per second, or we can write this mole per liter is equal to molar. So we can write molar per second. So for the zero order reaction, the unit of rate constant is equal to the unit of rate of the reaction, that is mole per liter per second or molar per second. After that, next is how we calculate the unit of rate constant for first order reaction. First order reaction, that is rate is equal to K, A raised to power 1 is equal to dA by dt. Okay, and here this is the differential equation. Then K is equal to rate divided by the concentration of A. Okay, and what is the unit of rate? The unit of rate is equal to mole per liter per second. Okay, students, the next is, what is the unit of concentration? The unit of concentration is mole per liter. These two are cancelled out and we got the unit of rate constant for first order reaction. So the unit for the first order reaction is equal to second inverse. After that, for second order reaction, next is second order reaction. It means it follows the second order kinetics. So the rate equation for this can be written as, rate is equal to, how we write this? K concentration of A is raised to power 2. Okay, then what is the unit of rate constant? Which is equal to the unit of rate divided by the unit of concentration term raised to power 2. The unit of rate is equal to mole per liter per second divided by, and the unit of concentration is what? It is mole per liter ka whole square. After this cancel out, one quantity is left here. Then we got the unit of rate constant for the second order reaction, that is mole inverse, liter second inverse. This is the unit for the rate constant for the second order reaction. After that, we come on the next, that is the unit of rate constant for third order reaction. Okay, and for this the rate equation is written as, that is the rate is equal to what? K concentration of A is raised to power 3, because it follows the third order kinetics. So the K is equal to rate divided by concentration of A is raised to power 3. So the unit of rate is mole per liter per second divided by the unit of concentration is mole per liter cube. After solving this, we got the unit of rate constant for third order reaction, that is mole inverse to liter square and second inverse. This is the unit of rate constant for third order reaction. So students, in this way we can calculate the unit of rate constant for any order of the reaction, for fractional order, for zero order, for first order, for second order, or for third order reaction. Okay, after that we come on the next. There is some important difference between the molecularity and the order of the reaction. Then what are the important difference between molecularity and order of the reaction? This question mostly comes in the board examination. The first is, it is the number of reacting species undergoing simultaneous collision in the reaction. Then order is, it is the sum of the powers of the concentration terms in the rate law expression. It is, molecularity is theoretical concept, whereas the order is determined experimentally. After that, it can have integral values only, whereas it can have fractional value. Then molecularity cannot be zero, whereas the order can be zero. The molecularity does not tell us anything about the mechanism of the reaction, whereas the order of the reaction tell us about the slowest step in the mechanism and hence gives us some clue about the mechanism of the reaction. It does not change, molecularity does not change with change in the temperature and pressure, whereas the order changes with the change in the temperature and pressure. So these are the important difference between the molecularity and order. So I hope all of you have clear your idea what is the basic difference between the molecularity and order. The molecularity is an theoretical concept. It is calculated from the balanced chemical equation. The molecularity is always in an integral value. It cannot be zero, it cannot be in fractional form. It does not tell us about the mechanism of the reaction, and the molecularity, since it is a theoretical concept, so it does not changes with change in the temperature and pressure. Whereas the order is an experimental concept. The order can be in fractional or in zero. So the order of the reaction is an experimental concept, so it gives us an idea about the mechanism of the reaction, and it gives an idea that the slowest step in the reaction is the rate determining step, because the reaction cannot proceed faster than the slowest step. And since the order of the reaction is an experimental concept, so it changes with change in the temperature and pressure. After that, you have clear your idea about how we calculate the unit of rate constant for the different reactions of different orders. Okay, so in short, for zero order reaction, for zero order reaction, what is the unit of rate constant? We have calculated that for the zero order reaction the unit of rate constant is unit of rate of the reaction, that is mole per liter per second. Okay students, then for first order reaction what is the unit? That is the second inverse. For the second order reaction, what is the unit of rate constant? That is the mole inverse liter second inverse. Okay, then for third order reaction, what is the unit of rate constant? That is the mole inverse to L square and second inverse. So in this way we are able to calculate the unit of rate constant for the reaction with different orders. Okay students, after then I would like to give you some home assignments. That is, in the first question you have to provide it with the rate law, and with the help of this you have to calculate the order of the reaction. Okay, the order of the reaction is simply you have to just add the powers or exponents to which the concentration terms are raised in the rate law expression. In the second is you have to calculate the overall order of the reaction and the rate law expression is given to you. After that, the third is you have to write the difference between the order and molecularity. In the fourth question, you have been provided with a gaseous reaction, that is the nitrogen dioxide react to give nitrogen oxide plus oxygen. Then for this reaction you have to write the rate of the equation, and a numerical is given in this part, that is if the rate of decrease of the concentration of NO2 is 4.0 into 10 to the power minus 13 mole per liter per second, then what are the corresponding rate of increase in NO and O2 concentration, and the answer of this is given to you. So students, you have to try to solve these problems and write in your notebook. Okay, that's all for today. Till then, be safe.